Hi folks, this video segment is going to be doing a problem using the 3D Experience FEA solver, and I'm going to be looking at the natural frequencies of a simply supported beam, which is under axial load. Now, uh, the, the purpose of these videos is to provide a forum for people who want to use 3D Experience uh, for doing finite element analysis, and they may not find sufficient resources on internet, and the documentation may not be sufficient enough for them to be able to do those problems. So here is one of the problems that I'm going to be looking at. Now, this problem is going to be done with beam elements. Of course, it can be done as 3D, but we're going to do it as a beam element with beam elements. And if there is no load, there is no axial load present here, the natural frequencies of vibration of this can be found in pretty much any standard vibrations book. However, if there is an axial load present, you have to look a bit harder in order to find the analytical solution for that problem. And I found it in this book, and notice that this expression, there is a P present. There's a P here. If P is 0, this term will go away, and whatever is left is basically what you find in most vibrations books, okay? But if there is a P present, obviously the expression is more complicated, and it comes from what you see there. I have divided this thing by 2 pi to change it into hertz. Ordinarily, uh, they, they don't have this 1 over 2 pi here. Something like that is given as omega n equal to, which is radians per second. But this is what we got. Now, the ends are simply supported. Okay, so obviously, if you have any other condition at the ends, this is not going to be applying. It is the data that I've taken is some values like this. So the cross section, I'm assuming that it is a square, 1 inch by 1 inch. The length of the beam is 20 inches long. And obviously, these are the standard strength of material formulas. The density is given here. I noticed that I could not specify a density like that uh, in this form in 3D Experience. However, there's this thing, and these apparently are the same, slinch per inch cube. Okay, and we're assuming the standard steel. We don't need the Poisson ratio because we're solving it as a beam problem. Now, if there is no axial load present, okay, as I said, there are analytical formulas, and you can do it on the program of your choice, and you're going to come up with the first 3 frequencies being these. Incidentally, I'm putting sufficiently restraints on this model that I'm going to make so that it only vibrates in one plane, does not come out of the plane, and it does not involve any torsional vibration. Okay? Uh, so these are the first bending frequencies. Okay? Now, what I'm going to do is I'm going to apply a load of 10,000 pound at the end tension. And you notice that the formula, this formula that you see there on the previous page, it predicts these values. Okay, these are also coming from that same formula. These are analytical results, and this is the analytical result for the case where P is 10,000 pound. Notice that the frequencies go up. Okay, this is something that if you think about it, makes sense. It's like a guitar string. When you tighten it, when you put a tension on it, the frequency of it is going to go up. It's going to be higher pitch. When you compress it by the same amount, the frequencies are going to go down. So no load, 10,000 pound tension, 10,000 pound compression. These are the analytical results, and we're going to be comparing the 3D experience model with this with these numbers. Now, the one thing you have to realize is that if you want to include, if you want these the effect of the actual load to be included, you must solve the problem as a nonlinear problem. Okay, so when we solve it, you make sure that the geometric nonlinearity is checked. If you don't check this, Doesn't matter how much tension you put in it, you always get the same frequencies. Okay, so we're going to do that problem. Uh, this approach that I'm going to take is not necessarily the best one, but we just want to see how basically a vibration problem, a simple vibration problem where there is the effect of initial load in it uh, has an impact is going to be modeled. Okay, so let's go ahead and do that. We're going to go into part design. Okay, and I'm going to create 3 points. Two of them to specify the geometry and one to specify the orientation of the cross section. So let me go here. Okay, so my first point is right at the origin. We're going to do another one, which is 20 inches away in the y direction. Okay, and then I'm going to create another one, which is basically 1 inch away in the x direction from this first point. So 1. Okay, good. So notice that we do have 3 points. These 2 points are going to be to define the line. What is it? Yeah, these 2 points are going to be used to define the line, and this other point, third point, is going to be used later on for geometry, cross-sectional geometry orientation. So a line from point to point, that takes care of this. And while we do that, I'm going to hide these first point and second point because I don't want accidentally to put some restraints on it. Restraints are going to go at the ends, not at those points. Okay, this is pretty much it. So let's specify our material. So we're going to go to Tools, create a material. I'm going to call this thing um, vibration, 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 axial load, axial load, and we make sure that the domain is checked here. Yeah, simulation domain is checked, which is good. And now we're going to say OK. This material is going to be created, but of course there's no information in it. I just have to fill it. In just a second, I'll be filling it. Okay, if I don't see it here, let me refresh the database. It's right here, vibration, axial load. So we can right click or just go with that arrow, say simulation. This is going to open up and we can input the stuff that we want. So structures, first of all, under the general option, the density is going to be specified. Notice that there is this thing called slinch. So I want, based on the number, based on the slide that I showed you, 0.4072 slinches. I think that's what we had, right? Yep, very good. And now we're going to go to Abacus Multiphysics, mechanical, elasticity, elastic, and I have 30 million psi. 30 million, 30, 1, 2, 3, 4, 5, 6. Is that right? Yeah, psi. It's interesting that I could not find the Young's modulus in the database. Uh, that's why it seems that it's stuck. Young's modulus being in units that you saw, this SI units. And this is not the only instance in the solver that I see issues like this, because basically it's the stripped version. The solver is the stripped version of the Abacus program, and they're gradually adding the documentation and any changes so that it's a transformed version of the Abacus program, but the stripped down version for sure. Okay, I don't need the Poisson ratio. And there we are. And now we're going to say right click apply. I don't need this anymore. I'm going to apply it to this part, check mark, green check mark, and this is it. It's done. The model has been created. Okay, so let me change the name of this thing. I'm going to change this thing to simply supported axial load beam. The axial load. All right, and we're going to save this, and that takes care of our model. So I'm going to go to the compass here, structural model creation. I'm going to use a blank FEM model basically. Okay, right there. Let's go mesh it. We're going to mesh it. Let's put 20 elements, so 1 inch long each. That's an overkill, but that's okay. So it has been meshed. And now we're going to go and create a cross section. So we go to properties. See, the properties are done here, 3D, 2D, 1D basically. Beam profile, we're going to choose a rectangle, a 1 inch by 1 inch, 1 inch by 1 inch. Say okay. And now we're going to assign the beam section. You click on the beam section, select the line. Notice that the line has been selected as a support. The material has been picked, and the orientation point is going to be this point. See that there is an orientation point here. Oh, let me see something. I must have messed up with something here. Double click on it. Let's see now. 1 inch by 1 inch. Okay. So properties, material. That's correct. Orientation. This is correct. Yeah. It's not showing up. So let me update. Something is wrong here. Beam section property is invalid. Okay, so let's check why. Beam profile. Oh, I don't think I selected the profile. That's right. So we go back to properties. I forgot to select the beam profile right there. See that? Beam profile. I forgot to select this right there. Right there. Beam profile, and there we are. Okay, we're good. So let's save this. And I'm going to hide this properties. Okay. Now we're going to go and create our scenario, structural model, structural scenario creation. So what I'm going to do is I'm going to, first of all, here on the finite element model, I'm going to select the model that I created right there. So the way I'm going to do this problem is first put tension on this, okay? And then I'm going to, once it reaches the end, that value of tension is totally applied, 10,000 pounds is applied, then I'm going to ask for finding the frequencies, okay? And this is why when we do the first static case, we must ask for linear analysis, because if you, sorry, nonlinear analysis, because if you do linear and then do frequency, that tension is not going to come into the picture. Okay, good. So let's start with the first one. Initial, let's see now, procedure. The first step is going to be static step. And yeah, so we're going to just leave things the way it is. We don't have to do anything fancy here. It's a very simple problem. And notice that under advanced, this is checked. Include geometric nonlinearity. Okay. I don't have to change any of these. As I said, this is a very simple problem. It's going to work even with a single increment. Now, as far as the strains go, let's start with this fixed displacement. So it's simply supported. So first of all, that end is pinned. So X, Y, Z are all fixed. Then now, and also I don't have any rotation about Y and Z. Some of these may be unnecessary, but that's really what happens. Okay, excuse me. All right, let's do another one. This end, this is on a roller, so it does not move in X, it does not move in Z, but it's free to move in this direction because actually we're going to apply attention to it. And again, rotation about Y and Z are 0. Now, the entire beam, we don't want it to go out of the YZ plane, okay? Out of YZ plane, we don't want it to go in the X direction. And also the proper appropriate rotation being fixed. So no displacement is X, rotation about Y and Z are 0. This makes it a fully two-dimensional problem. I don't know, two-dimensional or one-dimensional, depending on how you want to look at it. Okay, very good. And now we're going to apply a load of 10,000 pounds here. So we go to load, move this thing out of the way. There we are. In the direction Y, 10,000 pounds. So that's in tension. See that? All right, let's save this thing first of all. Good. Okay, so the second step is going to be a frequency step, but I can run this thing and then add the second step later on. I don't have to do it right now. I can do it if I wanted to, but I'm not. Okay, so let's go ahead to simulate. First of all, let's do a model check. Okay, let's do a simulation check. This is in case any gross errors are observed by the software. It's going to let me know and I'm going to fix it. But I don't think this is the case here. It's a very simple problem. This is still simulation check. And then we're going to do the simulation itself, which will actually find the deflection of this beam on the 10,000 pound load. Okay. We have not done any frequency calculation yet. Close that, and now we're going to run it. And we're not going to see anything fancy because it's going to stretch in one increment. It's going to stretch because I just total time, dummy time was 1 and increments were 1, and it can actually get to that endpoint in one step. Simple problem. You can see that there won't be any iteration, I think. I didn't ask for it unless, I mean, it may cut it down itself, but I did not. I specified the initial time to be 1. So it may do some iterations, but it's going to cut down that initial step of 1, not the one that I specified. Static step 1. Oh, see that? I don't think it required any iterations. Okay, so first of all, let's close this. Let me make this thing smaller. There. This is the initial step, initial increment, which was 0. And there is 1 mesostress. That's not a no-brainer because this is a, only axial load is going to be present here. But if you want displacement, change that to displacement. So this thing deflects by about 0.178. When you apply 10,000 pound here, it deflects by about 0.17, okay, millimeter. Sorry, I did not change the unit of this to inches, but that's okay. Okay, good. Now, first of all, let me, yep, that's fine. So now we're going to go back to scenario because now we want to do the second step, which is actually a frequency step. So over here, I'm going to do this frequency step, and I'm going to ask for three frequencies. You can ask for more, but I don't think it's needed because I'm going to be comparing it with only these. Say okay. All right. Let's. You can do a model check, scenario check, or you can run it. So I'm going to run it. So what happens here when this frequency check is made, sorry, this frequency step is run, it will take into account the fact that the structure was stretched by some amount. So it's going to use that information in order to calculate the frequencies. Okay, so let me close that. Let's look at the frequency step. See that? And it gives me three frequencies. And if you the first one which is here, it says 280, 248.62. So let's see what we had here. Let me make this thing smaller. So, yeah, something is seriously wrong here because these do not match. So it's time to go and find out what we may have done wrong. So let's actually go ahead. Let's go ahead and check some of the stuff that we inputted. First of all, as far as the material goes, let's check our material. Material. This line. Okay, so 7.2 e to the minus 4. Let's check that. Check what this thing was. Ah, 0.72. Ooh, okay. So this is going to be an extra division by 10. So that's minus 5. Okay. I'm pretty sure the Young's modulus was correct. So let's go ahead and run it. Yeah, things like this happen. Okay, so under scenario, we made a change in material. My density was wrong, so let's go ahead and run it. I should get as a first frequency 788. There was something around that. You won't get exactly this, but it should be close to 788 or something of that order of magnitude. Yeah, to within an acceptable accuracy. All right. Okay, good. So let's close this right there. You see this? 788, 788, 786 actually, 786, 786, 786 hertz. Let me move this thing out of the way. 788, and theoretical formula to 788. For the second frequency, 3D experience gives 2949 hertz. This is 2986 hertz. The third one is 3D experience gives 6468, and analytical solution is 6645. And these are all acceptable. Now, I'm going to change that. I'm going to change my load to minus 10,000 to convince you that we're going to get things in this ballpark. So let's kill this. Let's go back to our load. The force. Instead of plus 10,000, I put a minus 10,000. Minus 10,000. I'm going to run it. Notice that the direction is compressing it. The arrow is pointing to the left. Okay. Extracting results. Okay. Okay, so let's close this. Let's bring that slide out. Okay, so first frequency 668 3D experience. Over here is 669. Second frequency is 2833. Here it is 2867. And the third frequency 3D experience is 6357. Here it is 6526. All perfectly acceptable. Now, you might say, okay, well, is there a way I can check these? Because I never did it with no load. Yes, you can. And let me go there, close this. Let's go back to the load right there. Now, I can make this thing 0, but if I do that, uh, the program will complain basically. So I'm not going to make it 0 pound. I'm going to make it, how about, I don't know, 0.00001 pound, something like that. Okay, basically 0 pound, no force. Okay, so let's run it again. For all practical purposes, this means no load, no tension. And what we get should be very close to that first set of first column, first set of numbers. Remember, certain problems you may have to include the, uh, the, the stress effect, initial stress effect into the model. Otherwise, you get basically wrong natural frequencies. So to do that, make sure you solve it as a nonlinear problem. When you apply it, when you apply the loading in a static case, for example, you specify that it is a nonlinear problem. Okay, good. So let's close this. And right here, let's get back this. So you can see that 3D experience with no load essentially gives 729, almost 730, and this is 731. The second frequency is 2892. Here is 2927. Third one is 6413, and here is 6586. Perfectly acceptable as far as agreement is concerned. Okay, I hope you found this video segment useful, and wait, you're going to be getting some